continuous distributions of charge. And basically we need to go from point charges into large objects. I need to stop the buffering. Okay, so what we're trying to do, maybe I could go to some pictures really quick. Just instead of worrying about equations, I want to tell you conceptually what we're trying to do. Whoops, wrong way. I think I can see that now. Okay, and maybe I'll just adjust a little bit so everything right there. I think we got it. The idea here is we've talked about the electric field from a single point charge. And what we want to do is we want to take objects like rods, arcs, or discs of material and things like that, and we want to get the net electric field associated with this entire object. So if you take, for example, let me just do this really quick. You could imagine I take a rod or a meter stick or something, and if I rub it with fur, I might deposit some charge all over this. So the idea is, what if the charge is not just one single point, but instead it's distributed over an entire rod or an arc or a disc? The idea is simple. We pretend it's made up of little point charges. And then we get the electric field from each little point charge, and we add them all up to get the net electric field. All right? So in equation form, that would look like E total, when you add them all up, that's essentially doing an integral. An integral is summing over a bunch of tiny contributions. Oh, whoops. Let me get back on screen, sorry. There. So the idea is we're going to add up the tiny contributions. That means basically do an integral, and that means add up all of the tiny contributions from each individual point charge. So let's do a quick review here. K, Q, I'm going to say R vector over R cubed, or you could say it's K, Q, R hat over R squared. Either one of these would be acceptable. And so in practice, this tends to be convenient for computation, but maybe I'll use this one for the theory just so it matches all the textbooks that you use. The idea is, well, if I want, this is the electric field from a large charge, from a tiny charge, I just change Q to dQ. And all of our math that we had before is still the same. We still have to get the R vector and get the distance and the R hat or things like that, or the R vector and R cubed. But now we have an extra level of complexity. We need to figure out what dq is in each problem. Once we figure out what dq is, we can plug it into an integral and integrate it. And then, so maybe, well, let's immediately talk about charge density. So in one dimension, and maybe I'll go back to here just so you can see this all at once. Okay. Oops. Right there. So in one dimension, we typically use the symbol lambda. In two dimensions, we're going to use sigma. And in three dimensions, we're going to use the symbol rho to indicate charge density. Okay. So we think of this as charge per unit length, or the total charge on an object over its total length. And this is only strictly true if it's uniform. So I'll write that here. If the charge is uniform or uniformly distributed is really what I mean. Notice the units. In one dimension, we have charge per unit length, or coulombs per meter. So this is basically saying how many coulombs per meter. So if I put 70 coulombs on this 1 meter, oh my gosh, that'd be a lot of coulombs. But yeah, let's say I put 7 microcoulombs on this entire rod, also a large amount of coulombs. We would say it's 7 coulombs per meter. And that helps you figure out the charge in each little chunk. right? If you know the charge per meter, you can figure out the charge on 1 centimeter or 2 centimeters or any small chunk. You can see how this is going to help us with our dq. We split this into chunks. We use the density to figure that out. More in a second. Well, more right now. What the hell? Let's say dq is usually lambda dx. Now, to be clear, that's for a rod that's left or right. If it was up and down, it might be lambda dy. If it was an arc, oh geez, I'm on this dang. All right. Well, I'll get the camera right in just a second. But if you had an arc, we might need to use lambda. So let me just put it here. Here, dq would be lambda dx. Here, dq would equal lambda ds, where this would depend on a radius and a small amount of angle called d theta. So in these problems, dq is usually lambda r d theta, where you're going from, okay, anyways. But so this is showing you how we're going to have to do our integrals, right? We might have x integrals or theta integrals. Down here in this case, this is going to be a 2D object. More on that in a minute. So let me get back on the board here. Okay. Remember, our goal is to get dq, and so we need to understand density so that we can get dq. Right? So the last one we said was or. Oops. So these are the various ways we might write dq. This is for a rod that's horizontal. This is for a rod that's vertical. And this is for a thin arc. Okay? Those are the different ways we might write dq in terms of a 1D object. So notice 1D objects, we're talking about basically thin rods or thin arcs. Okay, those are the different types of 1D objects we're going to discuss in this class. 2D, sometimes we're talking about thin discs or thin washers. As an example of that, you can imagine this. You can already tell I'm going to split it up here in a little bit. All right, it's just a piece of cardboard, but you can imagine rubbing this with fur and getting charge all over it, right? So you could have charge on a thin disc. And then what we could do is we would want to split this disc into rings. Okay, and we get the charge on each ring and things like that. More on that soon. But in 2D, we're going to get charge over area total. And maybe I'll write the word area here just for this one time. And that's if it's uniformly distributed. So assuming the charge is spread out equally over all parts of the disk, that's what we get. Notice the units are going to be a little bit different. Coulombs per meter squared. And then dq instead of breaking it up like a small point charge, we're going to learn that dq is the small charge associated with a ring. So to clarify, this is a little bit different, and we will discuss how to do it in a few moments. We're going to start with this, and then we'll move on to rings later. But dq for a ring is going to depend on, now let's look at this thing. I'm going to have this ring, I'm going to build up an entire disk out of little rings like this. So the idea is this is my small dq. And when I add up this, notice it's 2 pi r around. That's the distance all the way around. The thickness of this ring is dr. And then I need to multiply by the charge per meter squared. So where am I going to put that? how would I write sigma 2 pi r dr? And again, I'm going to run through that. There's some area associated with the distance and the thickness. This is a 2D object, right? We're ignoring this dimension here. We're ignoring the thickness. That's why I'm calling it a thin disk, thin ring. And so 2 pi r is the distance around, dr is the thickness. You cut this, lay it flat. It's basically a rectangle of 2 pi r times dr. You multiply by this. Notice the units work out. Coulombs per meter squared times meters gives me coulombs. So that's a charge associated with this ring. Okay. Let's get this back up here. All right, whatever. In 3D, this would be charge per unit volume. Make sure that shows up on the screen. Looks like it just barely does. This is the Greek letter rho. That's not a subscript, that's just a letter. You probably know this, but whatever. And so to be clear, we're talking about total charge over total volume if it's uniformly distributed. All right, the units would equal coulombs per meter cubed, and dq would equal rho times some tiny amount of volume. And we'll go into this one more in detail later. So you can already tell I tend to focus on 1D and 2D for this class, but I will show you how to do this one later. All right. Okay, so that's our goal. We're going to start with these because they're the easiest. Now, maybe just to give you some motivation here, I think a visual will help. So let me see, I think I have one here somewhere. All right, so I'm going to run this and let's just watch what's happening here on screen. The idea is I'm adding more and more point charges, and each little point charge is contributing to the total electric field, in this case, at the origin. And what we want to do, if I run this thing again, hopefully you could see that. What we're going to do is we're going to try and do an integral, and the integral is the sum. And by adding together each contribution, we can get the total electric field. That's our goal. From a visual standpoint. What's cool about this, since we have the code open, maybe I'll show you this. The idea is in the code, this is your integral, right? We're adding to the total each time, and there is what where's what the calculus looks like in a computer program. And we'll be doing this in labs, so you can learn more about that. But notice up here, the charge on each ball or each sphere or whatever you want to call it is the charge density times the size of each ball. Okay, and in this case, notice, we could talk about this. The radius is half of the spacing, so the diameter. So basically, that's approximately right. So this spacing here is like your dx. It's the amount that we're changing. So this is the limits of the integral. Anyways, if you're into this, we will talk about this more in lab. But running it one last time here, the cool part about this, right, I'm going to actually show you this. Once you get this right, you can actually change the point of interest and it will redo the calculus for you at a different spot. And notice it's starting to grow up there near the top. So we could actually figure out the electric field at any point in space once we get this thing in the code right. All right, I think that's enough on that. All right, so let's do a problem. Let's see, where are we here? In the workbook, all of this is kind of described on page, I should have said that earlier. We're talking on page 19. So page 19 of the workbook. Sorry, I didn't say that right away, but it didn't really matter. Now we're ready to do a problem together. Page 19, 22.10. Come on. Okay, we're going to go 22.10. So let's just draw this up. Basically trying to redo that simulation. There's some object here. We're told in this particular problem, we're told that there's a distance here, A. There's a distance here, L. So those are the two distances involved. We're going to build this thing up out of a bunch of point charges. And rather than drawing all of them, I'm just going to draw one of these little point charges. So let's say we split this thing up into little chunks. And I'm most interested in this little chunk. So this is my chunk. I'm going to call this little bit of charge dq. Again, this rod has charge over the whole thing. And I believe in this first one, we're going to assume that the charge is uniformly distributed, spread out evenly. Uniformly distributed or spread out evenly. Okay. Well, since this is your first one, I'll just show you every step of the way here. We need to define where this charge is located. I'm going to call this X, the distance to my particular point charge. That's going to be important. There's also some size of it, which if I draw it this way, I hope this makes sense. dx is the width of that little chunk, okay? And because this is a thin rod, we're going to treat it as a 1D object. Obviously, this meter stick is not a 1D object, okay? This meter stick has 3 dimensions, but what we're going to do is we know all that really matters, and you'll see when the math works out, we can treat it as a 1D object and have this work out. All right? Where do I want to go next? So the whole point here is the electric field, and we're going to try to find the electric field at the origin. That's a vector, should equal the sum of all possible DEs. So we want to add up the contribution for each point charge. In this case, that's going to be dE, our formula for that is K dQ times R vector over R cubed. And that's it. In this particular case, maybe I'll mention this. Rod length is L, rod charge total is capital Q, I believe. Yep. So lambda in this particular problem would be Q over L. Again, because it's uniformly distributed, we can use that. If this was not uniformly distributed, we would not use that. Okay. Well, I know this has units of coulombs per meter. So if I simply multiply that by the amount of meters of my particular dq, I would get the amount of charge here. Said another way, dq should be this lambda times dx. Maybe to make this look pretty, I'll put this in red. The idea is you tell me how many coulombs per meter and how many meters long the segment is, I'll give you the coulombs. Piece of cake. All right. At this point, all that's left like every problem, is to figure out the R vector. Now, if you remember, let's talk about that. And maybe I'll color code this. Yeah, I don't know what color to use. How about I use this one? Let's see. I had some new colors here. Okay. Shoot. Anyways, I'll just use blue. Okay. In this case, the R vector. Oh, somebody's coming in here. Hey, oh, I'm in the middle of recording the lecture. Do you care?
No.
Oh, were you trying to? That was you trying to knock on the door, huh?
No, it was somebody else.
Oh.
I'm sorry to interrupt.
No, it's all right. It's all right. Just,
No, I'm gonna put her, I got a student that needs to take a makeup test. How long are you gonna be recording?
oh, geez, another hour maybe.
All right, I got a backup plan.
Okay. Sorry about that. Yeah. Good. Sorry, where was I? Okay. Oh, yes. Okay. So our goal is to do this problem. We want to figure out DQ. We've done that. We need to figure out the R vector. Got it. Well, remember that R vector is from what to what? Think. Pause the video if you want to take your guess. We need to go from the source charge. We're going from the source to the point of interest. In this case, the origin. I want to get the electric field at the origin, so I need to go from this charge to the origin. Notice this R vector is not X. It's X in the negative I hat. So for this particular one, my R vector is actually negative X in the I hat. Each problem, this might be a little different and this might be a little different. And that's what's every time. Oh, there's one other thing that's going to be different. I've got all the pieces to plug in. What are the limits? Well, at first you might not be able to tell. So let's plug in what all this stuff is before we try and figure out the limits. I'm going to have a K. DQ was lambda dx. That's my DQ. My R vector was negative X in the I hat. My R magnitude would be X. So the distance is X, but the R vector is negative X I hat. And now, gee, I bet you can figure this out. This isn't necessarily the standard way of writing it. Let's clean it up one more step so you can see it better. One of the x's is going to cancel. I get negative K lambda dx all over, what is it, x squared in the I hat. Check. Negative I hat K lambda. The x drops this down to a squared, and I've got a dx. Now, maybe you could tell what the limits are. We're integrating over what parameter? We're integrating over x. What's the leftmost value of x? Pause the video if you want to punch in the limits and then check. Okay, so you think what the limits are, then pause the video or whatever, yeah. Okay, here we go. The leftmost value of x would be not 0. The charge doesn't start until we get to right here. Well, that value would be x equals a. So the lower limit is a. The upper limit, we keep going. It's not L, right? This distance is a. I travel an additional distance L. So the upper limit is actually L plus a. All right. And that will give us the theoretical electric field. If you noticed in the code, maybe you didn't pay attention to the comments below the video, but I actually had the exact result. The exact result was based off this integral. The code only gave an approximate result because we were splitting it into a discrete number of chunks. The integral, in theory, is splitting it into an infinitely thin chunk, and so that's going to be a better result. Out of all this, just so I don't, well, let's go ahead and do this. I'll put it up. I'm running out of space. Let's put this up here. E at origin should equal, I'll pull everything that's constant out. What here is a constant? K, -1 is a constant. I hat is always to the right. Some unit vectors are not constant and cannot be removed, but the Cartesian unit vectors are always constants. That's one of the advantages of Cartesian coordinates. So K, -1 I hat is lambda a constant? In this problem it is. Because the charge is uniformly distributed, lambda is total charge over total length. These are not changing. As you move across, the total amount of charge that came from the fur is the same. The total length of the rod is the same, right? We aren't talking about x or dx here. This is the total length of the rod. So lambda is also constant. So that means I could rewrite this as negative k lambda I hat times the integral of dx over x squared from a to L plus a. Rewriting, you could brace me, you could check the answers in the solution. Negative k lambda I hat. Let's see, that's x to the -1. And I think we're going to get a -1 over x. Okay? We should get negative, so we, right, this is going to be x to the -2. We need to raise the power and drop that down. So that's why I got the negative sign. There's going to be x to the -1 with a -1. You can look that up, do your math homework. All right? And then just so this looks pretty, we're going to go from a to L plus a. Keep rocking. You know what? Why don't we cancel these two minus signs? So I canceled the two minus signs right here. And now I'm going to get, let's see, 1 over L plus A minus 1 over A. You could stop right there, but I think it's a better habit to plug in what lambda is, right? Lambda was not given in the problem statement. If you look up here, lambda was not, or if you look at your workbook, lambda was not one of the given parameters. Q and L were given parameters. So we should not list our final answer in this way. But since I'm lazy, I'm just going to replace this with Q over L. Okay. Now, this would be an acceptable form. I don't like it, and I'll explain why in a second. But let's say you wrote this down and you were happy with it. We should check a couple of things. If you want, you can pause the video and think, what things could you check? I claim there's at least 2 things we should check, at least with this result. Maybe, actually, probably 3. Okay, so see if you can think of what I'm going to think. All right, here we go. One thing is, we should check the frickin' units. What are the units of an electric field? Newtons per coulomb. What are the units of K? If we look that up, newtons meters squared per coulomb squared, that's the units of K. We've got Q, that's a coulomb. L, that's a meter. And then what are the units of all this junk? That's 1 over meters minus 1 over meters. Well, apples, if I take 3 apples plus 6 apples, I get 9 apples. So when you add or subtract, the units remain unchanged. Well, in this case, It looks good. The units check. Okay, the units match. What's another thing we should check? The direction. Now let's go back and look at this. If I'm at the origin, what is the direction of the electric field? Think, we pretend to put a plus charge here. If all of these charges were positive, right? If Q is a positive number, are we getting the correct direction? What direction should it be? If this is a bunch of positive charges, and I put a plus charge here, it should be pushed away. And yet, over here, we see a positive I hat. Is that a problem? No. Look carefully and you'll see big denominator minus small denominator. The small denominator term is larger than the big denominator term. So actually this thing is going to turn out negative and give us negative I hat. Woo! I'm sure that was keeping you up at night because, yeah, whatever. All right. Now, this is why I don't like that form. What I would actually do here is do a common denominator. So I'm going to actually just stretch this out a little bit. Hopefully this fits. I'm going to check if that's fitting on Zoom. Need to zoom out just a little bit. Okay. So the idea is I could multiply this term by A over A, and I can multiply this term by L plus A over L plus A. Now, when I do that, we're going to get K, Q, I hat, L times the quantity A minus L plus A, all divided by A times L plus A. Is that right? Yes. Right. Notice A minus A will drop out. We'll get a negative L on top. The negative L will cancel this L, but we'll keep the minus sign. So I believe we get negative K Q all over A times L plus A I hat. We get a result in the negative I hat. And that's a better way of writing it. That shows up. So we did two checks. We checked the direction and the units. And notice in this form, it's a lot easier to see that it's negative I hat. You don't, what is our goal as a scientist? We want to not only create results, but communicate them to others. And this is a lot more clear to someone else than that is. That's the benefit of writing it in this way. Being a good communicator will help you be effective as a scientist. Leaving it in this form is not ideal communication. The third check, this one's subtle. And as you get better and better, you're going to want to do this check. A limiting case. What happens if A is freaking huge? Let's go to the picture. If A is crazy big, maybe I'll draw a picture of this, right? Well, yeah. Let's just say I put the rod over here. I need a picture here. All right, so let's do a picture right here, just because this is the only spot I have space. If A is crazy big, right? Let's see if that's showing up. Come on, come on, come on. Okay, this would be a very, if I'm sitting here at the origin and the rod is way the frick over here, it's effectively a point charge, isn't it? If the rod is far enough away, if I could barely, if it's 16 miles away, it would look like a dot. Actually, I wouldn't even see it. But the point being, does this result make sense if A is huge. If A is huge, this term is negligible, and we get negative KQ over A squared. That looks like a point charge formula. So the last check, the advanced check, is basically think about what happens when you're far away, and does this object reduce to a point charge formula? In this case, it does. So that's let's see if there's anything else I want to say about this. I think we beat the crap out of problem 22.10. Now, some big picture, well, let me say some different things about this. So how might other problems differ, right? So how might we modify this problem and handle different cases? You could pick a different point of interest. If you pick a different point of interest, what should change? Think. If you pick a different point of interest, the R vector will be different. That would affect both of these terms. What if? Here's a different way. What if the charge wasn't uniformly distributed? What if it was non-uniformly distributed? That would affect lambda. If you're wondering how that would show up, that would look like problem 22.14 on page 20. You don't have to look at that right now, but I will show you how to do that in a bit. If this was non-uniform, typically what happens is instead of having to figure this out, you're given some function. You plug in the function and then do the integral as normal. So for non-uniform problems, it's almost identical, except lambda is a function that you plug in. All right. Here's an interesting subtlety. The default assumption is that Q is always positive when we're doing the derivation. After you complete the derivation, you could plug in a negative charge and this would still make sense. So by assuming initially that the charge is positive, at the very end of the problem, if it did actually happen to be negative, it's perfectly fine. Your derivation is still valid. You would just stick in a negative number and that would flip the sign here. So it's all good. That still works. What else could I do here? I think, oh, and if the object was located in a different position, let's say the rod was not located here, maybe it was in a different spot, that might change your limits as well. So from problem to problem, the things that catch you, you got to worry about the limits, you've got to worry about the correct R vector, and you've got to worry about the correct lambda. And most students, the most common mistake is screwing up the R vector. They accidentally go from the point of interest to the source instead of from the source to the point of interest. You always need to go from the source or from your DQ to the point of interest, wherever it is in space. All right, that really beats it to death. If you want to see if you know what you're doing, try doing 22.11. Okay, 22.11, see if you could set up the integral correctly. I just moved things around a little bit. I moved the origin and you could see. Or 22.12, that's one where I tried an off-axis POI. So most important when you're doing problems 22.11 and 22.12 is setting up those problems correctly. I could care less if you go through all the math to finish them, but for me, I did it. But I'm most interested in figuring out if you can set up the integrals correctly. Can you get the right limits? Can you put the pieces in the right order? Can you get the right R vector? So 22.11, 22.12 help you challenge it. Actually, 22.13 does that as well. I just switched it to the y-axis. So 11, 12, and 13 are good for you to practice. 22.13 you should do all the way through. 22.14 shows you how to handle non-uniform. I think you could do that. And also 22 points. I mean, geez. Yeah, there's all these problems between on pages 20 and 21. They're all just variations on this. I'll leave that for you to do. I really like, after you've done a couple of these, doing problem 22.19. And another comment, when we're doing these, sometimes you get ugly integrals, right? And so don't forget that on test day, I usually give an integral table like this.
So a lot of the integrals can be solved with this table, because obviously I'm not going to let you have a computer with internet connection during the exam. That'd be insane. But you could have these integral tables, and sometimes they use trig functions. And so if you get some experience and you look at the bottom of page 21, I give you some tips for different types of rods and the angles involved if you end up doing trig integrals, which are basically some of these integral tables on the back. So make sure you practice these. If you don't practice them, you're going to have a hard time on the test day. All right. And then since it's going to take me a little bit of time to erase, I might as well just stop here and start a new video for the rings and discs. So, okay, let's call that good.